Alright, guys, welcome back. So now today we're gonna discuss about this limits, which is topics of calculus. So we're gonna continue this section a little bit. Okay, now the definition of limits actually is an approximation. You can call it an approximation from left hand side, right hand side. So they're gonna reach to one point. Now, in short, this is the definition of limits, where you have a limit is written this way. So limits of x approach c over here. So there's a little arrow over here that x moving towards c. It means that x is approaching c from positive direction. And it didn't write any negative here, that means positive direction, as we assume that coming from the positive infinity side. So for the function of fx is equals to l. So any value over here that substitute into this function, you're going to get the approximate value. This is not the precise value, okay? It's just an approximate value, which is labeled as L. Okay, now if you look at this case over here, that this is some example that you want to estimate the limits of the polynomial, I mean the linear function of 3x minus 2. Okay, so this one, now if you list it in a table form, you can see clearly that if the point for x moving from 1.9 and 1.99, 1.999, 2.0, and start moving to 2.001, 2.01, 2.1. Now, from left hand side, right hand side, if you substitute the value into this function using 1.9, try with your calculator and see. For experiment, you get 3.7, 3.97, 3.997, and if you make it even more larger for the decimal places, it will be even closer to 4 actually. So it's close to 4. So now even from the left hand side also same, you're going to get the same result, which is near to 4, but it's just an approximation. So we know that the precise value is supposed to be 4, but for this case, since it's known to be limit, so we call that thing the value as just an approximation. Okay, so the concept will be it's moving from left hand side and right hand side. So like I say, if the limit is written this way, x approach to 2, it means it's moving from this direction. More precisely, it's coming from the positive side. So if there's a negative sign over here, that's from the negative side. I mean from this left hand side, which is far away from negative infinity. This side is far away to positive infinity. But for now we don't touch on the topics of the one-sided way of limits. So we focus just to explain the concept to you. This is what we talks about the limits. Okay. Now there is also certain case where you have this limits that might, how to say, is discontinued, and they have a different value, even though it exists in same location for the value of x, but you have different y value. So this case only happen for piecewise function, or possibly cases that involve absolute function like this. So you have absolute function, that means that thing might happens to be positive and negative. So now if assume that the case is positive and it's moving from the negative side over here. Now if you put this value from the negative side, you have the value as over here down to this level, and the other one over here, it's actually discontinued. Now it might happen like this if the function is a piecewise function, or the function that absolute. Okay, so that's this one we known to be discontinuous lah in the graph. Okay, so we are not focusing this much, but just to explain to you, there might happen this kind of cases in limits as well. So we call this as the limit does not exist. That's why so this thing does not exist, even though it's in x equals 0, but they have two different value. So If you get it from the positive side, you get 1. Negative side, you get negative 1. So the value is jumping over here. It's not precisely equals to the same value with the same sign, but instead it's different value. Okay, so it might happen. So some properties of limits and direct substitution. So the concept of direct substitution is actually coming from the example just now that we have the table. Okay, so like this, if you have the limit of x approach to c for this constant value, now as you know, constant value is a straight line, so doesn't care anything happen to the x value below, it's maintained straight line like that, so there's no effect in here, so the value still maintain the same. If this thing is actually a constant value, now if this thing is a function of x, then you just substitute the value c in, because they might have changes over the graph. Okay, then the third one, x power n, so the x will be replaced with c, and the same goes for the others. The x is only replaced over here, so just a substitution. You substitute the value of x approach to whatever value over here, substitute in, and that settles it. Okay, now regarding the properties, that one it's almost the same like the normal case for algebra. Okay, we can drag this constant value out, we can also split it to a different side. Okay, the limit can be separated to each of the items over here, or same goes for the multiply, even for the division, and even for the power as well. All of them are the same, so you can do it that way. You can totally follow the properties. And now we look at this example 9 on the direct substitution. Okay, this is a case where you can directly substitute the value and you get the value for this cases, or the answer. Okay, like the case over here, if the x is approached to 4 with the function of fx is x squared, just substitute the 4 into here and you get the result as 16. The same goes for the rest of the other as well, where over here you substitute the value of x, which is equals to 4, and we get 20. Trigonometry function as well, so we just substitute the value of pi in, where you get 10 pi is equals to 0. Over here you get equals to pi, because this is just x only, so you get pi, and that's 0 over here, and the rest are the same. Now our main focus is just to substitute the value of x into the substitute the value of x over here with whatever value that's given in here. So we just put it over here and we get the value as display over here. So these are all the value that you just direct substitute in and you're going to get the result. Okay, now for computing the limits, okay, now if we want to compute for the limits over here, there is a few possible, there's a bit of using of the properties. Okay, you have a choice that you can directly substitute this value 3 in and get the result. You're going to get the same result, or you can split the thing up using the properties of limit one by one like this. Okay, and only then you substitute the value of x equals 3 into this x function over here and get the result. It's both the same. Now just experiment it. If you substitute 3 into here, you get 9 plus 1 equals 10. Now this is a case where you didn't split it like this, you still get 10. If you split, you also get 10. So the same goes for here. If you without doing the separation over here, you're gonna get the same result by directly substitute the value in. Now this is only for the case that if the denominator doesn't happens to turn into 0, then it should be okay, it should be fine, you can use it. But if you check the thing, you substitute substitute the value of 1 into here, and suddenly you get the denominator equals to 0, then this method is not usable. So you have to use the other way around. Okay, so now let's see this situation over here. This is what I talked about just now. If we have this, this is what we call the indeterminate form. If you substitute the value of the limits of x, which is equals to -5, into this function, what you get is that the value turn into 0. So, so this question is designed to be upper and lower level equals to 0, but the main important thing is the denominator must never be 0. So if it's becoming 0, then it's unsolvable. So how are we going to solve this kind of cases? Okay, now if you look at it, if you substitute this -5 in, you get 0. Okay, so how we solve? Now normally the factors of the function given over here, now for our main case over here, usually you can find the factors from the tops, the denominator over here. So this is the denominator, this is the denominator. So from the denominator, you can actually get the hint to factor whatever polynomial below. Okay, so quadratic function or whatsoever, you get the hints over here. This is one of the so-called factors for whatever comes around here. So like this one, x plus 5, meaning that below there might have possibly, okay, the factors of x plus 5, and if we factor this thing, yes indeed we have it, which is x minus 5, x plus 5, so that gets you x squared minus 25. So from here we can cancel this what we call the terms, and change into 1 divided by x minus 5. Voila, now you can substitute the value of x, which is equals to -5, into it, and you have the result as 1 divided by -10. So no longer you are getting any zeros over here, solvable. Okay, now let's assume that we have another case which is involving infinite. This is a case where you have the limit moving to the infinity, which is normally people will say this is hard to solve because the value is too big, but it's actually solvable. So if you look at this example over here, we have the function of 3x squared plus 5x plus 1 with divided by 2 minus 4x squared, where the x is approached to infinity. Okay, now even though it's approached to infinity, and if you directly substitute this value in, of course you're never going to solve it, because we can't find the precise value where the number are so big divided by another big number. We do not know how big the number that is, so we are not sure. Let's say, let's give you an example. Let's say you say this approach infinity, maybe this is a 10-digit number and this one is a 9-digit number, okay, divisible, but what is the precise value? Unsure. Now maybe this is a 9-digit number, but this one is a 12-digit numbers value as a denominator. You also unsure what is the precise value, which is 0. whatever, so unknown, because infinite value is big, very big, and we cannot actually get the precise value, and what we want here is to get the approximate value, so as possible if we can. So we don't want to leave the thing as infinite divided by infinite, which is also an infinity value, not sure. So what we can do is simply look through this terms over here, the fraction, so polynomial fraction over here. Look for the largest powers of the x and take that as your divisor. So you're going to divide this thing for, I mean, the whole terms from upper level and lower level with x squared. Now if you divide it that way, it's going to turn this thing, if you divide all, I mean the upper level and lower level with x squared, this is going to turn into 3. This will become 5x divided by x squared. So what we get is 5 divided by x. This one will be 1 divided by x squared, and the same goes for the below this thing as well. Once it's divided by x squared, it's gone. So now another possibility that you can see is, I just want to ask you, if you take 1 divided by 1, 1 divided by 1, you get equals to 1. 1 divided by 10, you get 0.1. 1 divided by 100, you get 0.01. So what if 1 divided by infinity, which is so big number, you're gonna get 0.000 something so long of 1 possibly. So which can be totally ignored as equals to or approximate to 0. So we're gonna leave it as equals to 0. It's not actually equals 0, but it approximates 0. So in the terms over here, we just leave it as 0. Okay. So when you divide by x, which is a very huge numbers of infinity, this term will turn into 0 as well as this one 0. This also turns 0. It doesn't affect constant value, so constant value remains the same, and we have the value now. It's solvable. Okay, now we are looking out for the dividing out technique. Okay, now the dividing out technique is a technique that it also happens to be same situation like the indeterminate cases, where when you substitute the value of this limits of x into the fraction or the function, you're gonna have the problem of getting a denominator equals to 0. So we have to find and figure out some way to solve this thing. So as you see, -3 put in here, 0. So it's unsolvable. Even with calculator, it's not solvable. So what we do is, we're gonna figure some way out, and again get some clue over here. So usually whatever lah the denominator or the nominator, which is the short version of this term, usually that is the hint for finding the factors. Okay, so like this case, the upper level is higher power of polynomial compared to the below, so we're going to take the below one as the hint to create the factors for the upper. So let's see if we turn this thing up. Now this is x plus 3, we just put another brackets of x plus 3. So what multiply with something over here, you get 6. 3 multiplied by 2, right? So you get 6. But which one that you have to put positive or negative over here, that you can have a positive number over this side. Okay, even though you get a 6, but it seems that if you put a positive value over here, that's never gonna happen to have a negative. So the best choice is put a negative sign over here, and there you go, you have a factor. Just double check again, multiply, and is it you're gonna get x squared plus x minus 6? Yes. Okay, now if it's okay and good to go, then we can proceed with the elimination. So this x plus 3 and x plus 3 are the same, so we can eliminate this thing, and moving down to only x minus 2, and now we can substitute the value of -3 into it, and we have the result as -5. Okay, so another one of the dividing out method. Okay, so these are the same. Again, I'm gonna use this the smaller one from the denominator as a clue or hint to guide me to do the so-called factoring for this function. So as you can see, this is x squared minus 1, and look at the upper denominator. Yes, there's a possibility you might get the same terms below by dragging this x out, so you get x, and this is x squared minus 1, so this one can eliminate, and there you go, you have x, and just substitute the value and solve the thing. Okay, this is another one, same as I say before, take the term that is shorter. I don't care the thing is below or upper, that is your clue, actually a hint, a clue or something. So even if it's a denominator or maybe nominator, it still can be used as a clue or guideline for you to find the factor for the long polynomial terms over here. So we take this x minus 3 as a clue, and we try to create another one over here by putting x over here, the sign unsure, but we try to find the factor that gets you 6 over here, which is 2. So now look at this one, you get the positive sign, meaning that since one of the sign over here is negative, it's not possible you put a positive over here to get a positive sign over here. Positive with negative multiply together to get a negative value. So the only option is negative. So this one can eliminate, and we have x minus 2, and when we substitute the value of the limit x equals 3 in, voila, you get the result as 1 over here. Okay, so now we're gonna moving to this example. Okay, so this one is a bit longer. Now you don't have any clue how to find this, since both of them, the upper level and the lower level, are, I mean, at the same levels of power. So what we do now is we're trying to find any similar factor. We just simply factor this to the lowest, how to say, the lowest combination of factor possible, which is over here is 3, 2. This one, we try to find anything that relates to, I mean, the smaller number. You cannot take 12 multiply with 1 because that's a very huge number. Okay, so you cannot take 6 and 2 as well. 6 and 2 also quite big because 6 is big. 6 times 2, 6 is quite big. So we try smaller one. What else is smaller one for getting 12? So the smaller one is 4 times 3. Okay, so now we're gonna try factor this thing out. So factor this, what we have is this one over here, we get 3 and 2. Okay, 3, 2, we get 6, but since the signs over here are all positive, so that means we're gonna put the sign as positive as well. So for the below, we got 3 multiplied with 4, which is 12, but the sign positive and negative still unsure. So we're gonna look at the medium, I mean the center point over here, which is negative 1. So if negative 1, we have this 3 times 4. So if we put negative over here for 3, and this one as negative as well, you're never gonna get negative over here because negative multiply negative, you get positive. Now the same case, if both positive, you're also never gonna get negative. So either way, you're gonna check either this one is negative, this one is negative, or this one positive, this one negative. So there are two flip over here. So we assume that if, let's say, you have 3 as negative and this is positive, so negative 3 plus 4, you're gonna get positive 1. So this is not a positive 1, it's negative 1. So we exchange the sign and turn it into negative. This is positive, then we have negative 1. So double check again, multiply this and check is it's similar with this term over here after you multiply in. Yes, so it's correct. Then we can move on by eliminating whatever that you can eliminate from here, which is x plus 3. So now we have x plus 2, x minus 4, and to substitute the value in, you have the result as 1 over 7. Okay, so now we're going to moving to the rationalized technique. So this is a refresh, I mean just a review for the topics since it's already taught in class. So I hope this video might help you in studying this method further. So who knows, you might miss out some methods during the class while you're getting distracted possibly. So this could be a good way to refresh back all the methods. So even though I go through a bit fast, but just revise the thing for the method and technique. So for the rationalizing technique, actually what we did is, this is a similar situation like the indeterminate cases where you have 0 as well, or maybe it turned into an unsolvable cases. So what we did is we're gonna use the method called getting the conjugate and multiply. Now this is one of the way we use it. So let's say you have this as square root of x plus 4, and your conjugate will be square root of x minus 4. So usually the changes of sign, the sign positive and negative, only happen at the constant parts over here. So not only that that I might get wrong, possibly if how to say, if you have this thing in the flip side, anyway, there's a sign changes over here in the center. So you have the conjugate, where this is what happens over here. Okay, now we look at the example. Look at the example over here. So we have to find the limits of square root of x plus 1 minus 1 divided by x. Okay, this is the case now. So if you substitute the value of x approach to 0 into it, what you get is actually straightforward a 0. So it's again unsolvable. So what we did is, obviously you can see this is unsolvable. So what we did is over here, now since you know this function over here and the one behind here is actually multiplied with 1, so that's something multiplied behind here which is equals to 1. So if you can see this, after the divide you also get 1, so it might possibly become 2 divided by 2, 10 divided by 10, 1000 divided by 1000, but it can be anything. So why not we put something that beneficial to get making the function solvable. So what we did is simply that we put the what we call the conjugate of this function over here, the square root term, we assign another one over here which is a positive, empty this function over here, okay, and we put it as a pair like this one. You're going to get, after division you get 1, so it doesn't affect the equation at all, doesn't affect anything, but it did affect the shape of this thing in the end, but it doesn't affect the value. The value maintain the same, but the shape of the function might look a bit different. So at least it make it solvable. So what we do is we just multiply this thing in. So the square and square multiply together, we get x plus 1. This one we get negative 1, and this one we have x multiply with this terms over here, square root of x plus 1 plus 1 over here. So now this is the final form of the term. Okay, not yet final lah. There's one part that I forgot to see. I kind of miss out, which is the x can be eliminated. Okay, so once you eliminate this, you have the term as 1 divided by square root plus 1 over here, where from the above, suppose that x not supposed to equal 0 because it's unsolvable. But now, once you turn it into this form of the equation, from here turn into here, if you substitute the value of x equals to 0 in, it wouldn't bother. You're going to get the result. Okay, you substitute 0 in. Now this is what you can see. You get negative 1 divided by 2, and that's it. You get the thing. Compared to the previous original version, when you substitute the value of x equals 0, not possible to solve. But here, yes. Now this is one of the trick that you can use. Okay, so now this is a I think this is a last example, I guess, not sure. Okay, this is another example I just want to show. Now, same format, same technique that you use. If you have this as square root x plus 4 minus 2 divided by x, again x below, if you direct substitute, you're going to get 0 and unsolvable. So what we did is we add the conjugate over here, which resulting equals to 1 after you divide the thing. So we make something benefit out of here, which is the anti of this. Just like antivirus, there's a virus, there's an antivirus, so there's an anti form for this function. So when we multiply this thing, I didn't show the full multiplication anymore since the previous example already showed it, so you can refer back to that in the video. Okay, so over here, once you multiply, you get the form like this. Okay, now suppose there's an x over here, but it's already eliminated from the upper and lower level over here. Substitute the x equals 0, and we have the result as 1 over 4. Now the same goes for the rest as well. Even though we change the value x turn into 9, but still we get the same result equals to 0 over here. So what we did is same method. So you're gonna look for the parts over here where you have the square roots. Okay, this is the main, the star of the system. So you're gonna look for the star. Okay, now this one over here, find the conjugate. Okay, since it's negative, so here we're going to put it as positive, and of course we're going to put it in up and down like this, a pair, so that the division, when you divide it, is equals to 1. So now after multiply and eliminate some of the terms, this is what we have over here. Okay, so this is what we have. Okay, now you substitute 9 in, you have the result as square root of this is equals to 3. So 3 plus 3 is 6, and then you have the thing. You have the result as follows. So okay, now number 8. Okay, this one. Now this is infinite, so this is big. Now compared to the previous one, this one you are not required to use the approach for, multiplying with the conjugate. Why? Because you don't have any square root terms over here. The function that involves square root is not here, so we're going to look for other alternative. So if we substitute this, we're going to get infinity divided by infinity. Okay, done. That one cannot be solved. So what we did is, again, like I told you before from the previous example, we're going to find the largest power over here, which is only x squared. So this is x squared is the largest one. So we're going to divide this from the upper top level and lower level over here with x squared like this. So divide this thing, and what we have is the upper will turn into 1. This one will become 3 divided by x squared. This one will become 1. Now, like I say, if you substitute infinite to below, so a number divided by something, a very huge number, you're going to get the value almost approach to 0, or you can say it's 0. Okay, so small. Okay, so this 1 divided by -1, you're going to have the result as -1 over here. So it's solvable. After you convert the form from the normal function into here, it will turn the limit into a solvable